All right, calculus, you have reached the last video of regular stuff. I think I'm going to make one more video to help review, but man, here we are. So we were talking about like finding volumes, right? That's what 7.2 is on, is finding volumes. And basically all the problems from yesterday were where, oh, this is 7.3, sorry. This is where they kind of gave you a picture and you could see what the cross-section looked like. Today, what happens is they tell you to maybe revolve something around an axis, which gets a little bit crazy. So I'm going to actually end up moving the camera around a decent amount. Alright, today so you can see this, because for instance, the very first problem that we're going to tackle is it says something that there's a region in the first quadrant bounded by the y-axis, y equals cosine x, and y equals sine x, which is kind of weird because cosine starts here, right, and it continues and goes down or whatever, and sine starts here and continues and goes up. So they're actually saying just this little piece, right, which they'd actually meet at pi over 4, I believe, right, because that's where sine and cosine are the same. So they're saying this little piece right here, that's obviously not a volume, that's an area, right? And we could find the area of that thing by doing 0 to pi over 4 and doing cosine on the top minus sine on the bottom, right? And we find the area. But they don't want the area. They're saying revolve that guy around the x-axis. They usually say about, but that means around the x-axis. And then they're going to say, find this volume. Now you might be like, okay, what does this even look like? So the best I have, I was going to have you guys actually use the 3D printers this year, but alas, what can you do when school's out? This I realize is not, I realize this is not a cylinder. Basically my example is going to be if this thing looked like a box right here and we revolved this about the axis. Okay. So it's going to spin. So essentially, what you have to visualize is if this is the x-axis and the x-axis spins, okay, this would make a cylinder, right? It would sweep out a cylinder in space, all right? So if you did this, this thing would go around and it would come out of the board and back into the board. So that is what the solid is. So if it was this, this would actually be really easy to find the volume of because you'd see that each cross-section would be a circle. Again, which we did some circles yesterday, we did some squares, right? So you'd see that each cross-section would be a circle. And so you'd be able to do it. But with this shape, you're like, what in the world, right? This thing's going to come out and come around, and it's like, I guess it makes some sort of circle, but it's like hollow on the inside. Like, what does that look like? So the best I have is that the book actually tried to model this. So I'm going to go over to the notes that I have on the computer and just kind of show you guys here, if I can. So they're saying it would look something like this. And I don't even know if that's a good picture or not. But basically it would be circular, but there'd almost be like a hollowed out cone in the middle. And then what they have in pink here is actually what a cross-section would look like. And if you notice, the cross-section almost looks like a washer, right, that you'd like use when you're putting in screws, you know, and bolts and stuff. So obviously I sound really educated on that, but the only thing I know about washers and bolts is when I build the set for the musical, so there you go. But basically, what is the area? Because remember from yesterday, we're going to need bounds, and we're going to need the area of a cross-section. Well, the area of a cross-section, in this case, if it's a washer, right, is going to be the area of the outer one minus the area of the inner one, right? And then we're going to take the integral of that. This ends up being called the washer method a lot. You can probably see why, because they figured that you're going to have to find washers a lot as far as your cross-section if you do something like this. So let's go ahead and try this thing and see what we got now that you've hopefully seen it. These do not end up being very hard, but we do have to make sure we're very careful to like try to wrap our heads around visualizing, and that's the hard part. The integrals are not that hard themselves. So when we revolved this, we saw that we would probably have a hollow part, and then we'd have a big part that would come sweep around the outside, right? So it looks something, oh, I just totally did that wrong. There we go. That looks much better. And this thing would sweep around the outside, right? So we're going to have a washer. So the integral then ends up being from the bounds, which is 0 to pi over 4, because that's where they're meeting. We didn't go past that, right? And we need the area of a washer, right? And we said the area of a washer is pi r squared of basically the outer r, right? If we wanted to find the area of a circle, we'd do the area of the big circle and then subtract out the area of the small circle. So it's like we've got two radiuses. Sometimes in the book that you'll see them use like a capital R to make sure that they're saying, okay, there's the big radius and there's a tiny radius. Now the question is, what are the big radius and the tiny radius on our picture? Well, the big radius is just the height of the top curve. Well, what's the top curve? Cosine. And height is just whatever that function is. So this actually is just cosine, right? And then what's the radius of the small one? Well, the radius of the small one is just whatever the bottom curve is, which is sine. So there we have it. We've got the integral from 0 to pi over 4 of pi cosine squared minus pi times sine squared. Man, I'd love if this was a plus, because then I could just turn that into 1 and pull out the pi. But this actually happens to be something that I think we will plug into NINT. And I will let you guys do this whenever you are doing a volume that you have to visualize and revolve it around. I'll just let you use NINT. Deal. You don't even have to do it by hand, because there's a lot of things that you're going to be taking care of anyway. If you want to do it by hand, they'll be my guest. I know some people probably will want to. So let me see here. Let me plug this into NINT for us, if my mouse works here. So 0 to pi over 4 of sine squared, sine x squared minus cosine x squared. Oh, I'm supposed to do it backwards. My bad. So you get half pi. Huh. Because before I put the pi in there, it came out as half. So, lo and behold, that's crazy. You'd get pi over 2. There must be a good way to do that one in your head then. Oh, I bet it's using a trig identity. Now I see it. You could pull the pi out, and cosine squared minus sine squared is actually the same as cosine 2x. Because that's an identity, and that's really easy to go backwards from. Huh. Well, there you go. Could have done that one in our heads, but that is A-okay. Alright, so here we go. We got to see another one, though. Alright, we just got to see several of these, I think, before we feel comfortable doing some. So, let's see if we can visualize something being revolved around an axis and find our points. Sorry, I keep getting up and sitting back down, but I think this one's kind of pertinent to be able to see things. I didn't want to do it on the iPad. I said I'd give you an easy one on this one. So it says, find the volume of a solid created by revolving the line y equals x. That is pretty easy. Boom. About the x-axis in the interval 0 to 4. So from 0 to 4. 1, 2, 3, 4. So if we revolve this around the axis, it's this whole thing we're revolving around the axis. This doesn't even have anything to take out of the middle, right? So if we revolve that, just so you know, what's really nice about revolving is it's always going to be circles, right? When you revolve something, it doesn't just like turn into a box, okay? It sweeps out. So it's either going to be, today when we're finding our cross-section, it's either going to be a circle or it's going to be a washer. Okay, it's not going to be a square or a triangle or anything weird like the first part of the homework where they drew the cross-sections on there and it could be anything. When you revolve something, it's going to be a circle. So this one's so easy because what are our bounds? Well, they said on the interval from 0 to 4, so that's our bounds. What's the cross-section? It's a circle, so this is going to be pi r squared. We just got to figure out what that r is in terms of x. right? And what's the radius? The radius is whatever the height of that is, which is just our function, which is just x. Bam! No wonder I said this was such an easy one. And we could definitely do that in our heads. We'd have 1/3 x cubed with a pi from 0 to 4. So it'd be 64/3 pi. Wow. That was an easy one. Let's step it up a little bit. I mean, it kind of, if I could have let you do it on your own, I guess that would have been different, but I can't do that, I guess. So this one looks a little bit harder. Let's see what we got. It says, find the volume of the curve bounded by two different equations again. Not sine and cosine this time, so by y equals x squared plus 1 and by y equals x plus 3, revolved about the x-axis. We can do the y-axis as well, but we'll get there in a second. We're going to stick with the x-axis for a minute. So, and does it give us an interval? Nope. So I'm assuming these cut into each other somewhere. Let's find out. So this guy right here, I know is a parabola that starts up 1 and does the normal parabola thing. So 2, 4. So it does this, right? It's going to go up. And same thing over here. And then it says this guy. So I'll graph this guy in blue. Up 3, up 1 over 1, up 1 over 1. Oh, look at that. They made it meet so nicely, right? And they're saying revolve this shape around the x-axis. So that is what's going to be super bizarre. Alright, because at least right now we do know something, right? We do know that the bounds are going to be from wherever they met. So that's 1, and then that's 2. So that's -1 to 2. So at least we know that. And we know we're going to have some sort of pi r squared, because I told you everything's going to be a circle. What I usually do is, since we don't have the book where we can just draw things 3D, but what I always typically do is I at least draw the mirror image down here underneath the axis, alright, and do something like this. Because then at least I can visualize, oh, this thing's got to go around, right, like this. It's got to go around. So the main thing is it's either going to be pi r squared, or it's going to be a washer, pi r squared minus pi r squared. Now, how you can tell which one's which is the one we just didn't have any space in the middle, right? It was just a solid, like, pyramid type thing. This has space in the middle, right? It's hollowed out. So we know it's going to be a pi r squared minus pi r squared idea. We just got to figure out what the radiuses are. Well, what is the big radius? The big radius is like from here, because the radius, it's always the axis, I always said. Big radius is from here to here. So that radius is the height of what? The line. So we're going to have the integral from -1 to 2 of pi, and then the line squared, right, minus, what's the tiny radius? Well, the tiny radius is just from, you know, here to here. That's going to revolve, right? If it was here, it'd be like here to here. So that's the parabola, right? So the parabola is that second radius. And again, I'm going to let you plug it in. This one totally you can do by hand. You'd have to pull out the pi, you'd have to FOIL both, combine your like terms, then go backwards, and then plug in your -2 and 1. But again, since there's so much visualizing, typically on these, what I let people do is I just say, you've done a lot of visualizing and figuring out what the problem looks like. I won't make you FOIL everything and make sure you've got it. So, plug it into Mint. Math 9, -1. 2. And then we have x plus 3 squared minus, you do just got to make sure you got the right thing on top, because that's not going to help if you don't. X squared plus 1 squared dx and then I'll take it times pi afterwards. It's apparently 23.4 pi. Now remember, the reason I can take it times pi afterwards, I didn't plug this into int, is because since it comes out of both of them and it's a constant, it could come out here and just do this, right? That's what I plugged into int, and then it's 23.4 pi. So you could do this all by hand, and that's 23 2/5, by the way, so you could have like a fraction pi as well. But there we go. Boom. So these are like circles or washers, peeps. That's kind of what's going on. Next one. I think we got 2 more left. Obviously the last one is the hardest one. But this one is, I said that we can go around the y-axis. So that's what we're going to do. Here we go. So this one is actually a really easy shape again. But it's around the y-axis, which gets a little crazy. So let's see here. It says find the volume of the solid generated by the triangle with vertices at 0, 1, boom, here's 0, 1, 1, 1, 1, 1, and 1, 0. So this triangle, and they're saying revolve it around, instead of revolving around the x-axis, we're going to go around the y-axis, right? So I sometimes just draw this in here, right, just to help me visualize. So even though we're going around the y-axis, and we'll talk about what that means in a second, we can already say if we're going around here, is this going to be a washer or is this going to be a circle? Well, this is going to be a washer, right? It's going to be pi r squared minus pi r squared because it's going to have a bigger radius and an open area. Now notice if I put dy right here. Basically what you need to know is if you go about the y-axis, that practice that we got last section when we were doing area with y integration was for this right here. Alright, if you go around the y-axis, you have to integrate with y, which means your equations have to be have x by itself instead of y. So that's really interesting. And again, you kind of need to look at it sideways, right? So where are our bounds if we're looking at this sideways and basically going from bottom up? Well, from 0 to 1 are our bounds, right? I mean, technically it's this way, but that's because all the points are 1, 0. But it's because we're going from here up, right? And then, once we have that, what is the bigger radius? Well, the bigger radius is this guy right here, right? And this equation, what's this equation? Well, this is the equation x equals 1, right? Which is great because when you do y integration, you don't want y by itself, you want x by itself. So what's crazy is the first radius is just 1 squared, and that's because this is that equation, right? Now what's the smaller radius? The smaller radius is actually the area, or the equation of this line, but that's the line y equals x. But that's just means that's the same thing as x equals y, right? So we need to do minus pi and then y squared, right? Because y is that one. And then that's dy. This one's actually going to be super, super easy to integrate, but I wanted to make sure this is a weird one to see. You got to visualize going from bottom up because you're going around the y-axis, so you're adding up all the circles this way. So that's why you have to have a dy. So whenever you do y integration, y-axis, you got to have y's everywhere, which means you got to have x by itself, right? So that you can put y's in your equation. This one we can totally do by hand. I'm going to pull the pi out, and it's because there's no foiling. This is nice. It's just 1 minus y squared if we pull the y out. And we can go backwards from that, right? Y minus 1/3 y cubed from 0 to 1, and 0 is going to just get 0. 1 is going to be 1 minus 1/3, which is 2/3, and then I've got a pi on it. That wasn't that scary. Whew. There we go. Alright, we got one more. Doing great, hanging tight. So this one is going to be super crazy because it's still volumes, it's still revolving, but it actually does not even have us revolve it about an axis this time. It has us revolve it around a different line. So it says, Find the volume generated by revolving the region bounded by y equals x squared and by y equals 1. So let's take this here. So y equals x squared is actually just a normal parabola, so that's pretty easy, right? And then boom. So it's this and this. And actually y equals 1 is just this, right? Boom. So here is our thing. And I'll shade this in. Now if we're going about the x-axis, a good thing to notice is we'd be doing the washer method, right? We have pi r squared minus pi r squared, because that would be that. But here's where it gets crazy. Because instead of doing the washer method, they say revolve around y equals 1. So actually saying let this line, which is parallel to the x-axis, they're saying revolve around this line, which means this would just kind of look like this. This would be like this, right? So this is just something that looks like a little football, really, when you stop revolving around it. So this, if you notice, there is no hollow space in here. I'm going to stay with green, actually. So we're going to do two problems here. So this is just a pi r squared example, right? And what are our bounds? Well, we know the parabola and the line meet at -1 and 1. So it's -1 and 1, pi, and then what's the radius, though? That is the tricky part, right? So what is the radius of this thing? The radius of this thing is this, or I could draw it in here. Now, the reason I'm probably going to want to use the bottom one instead of the top one is I can see, oh, even though the radius isn't a height from the axis, because whenever it's a height from the axis, we can just use this, but the radius does go from blue line to blue line, which means all we got to do to find the radius is find the difference. And the difference between this and this is just 1 minus x squared, because that's the top curve and that's the bottom curve. So this is -1 to 1 of pi, and the radius is actually 1 minus x squared. But we still have to put a squared on that because it's pi r squared, and this is actually your whole r right there. I'm not going to nint these yet. I'm just going to hold on to it. So that's actually when you revolve it around y equals 1. What if we get dangerous, very dangerous, and we revolve around y equals 2? Now notice you might be like, why aren't we using y integration? Whenever you're going the same direction as that axis, right? Y equals 1 is the same direction as the axis. So that's when you use x integration, is what's going this way. If it was revolving this way, we'd use y, but it's going the same way as around the x-axis. Now here's the thing, we don't even have y equals 2 on our picture, right? Let me get rid of all this stuff and redraw my blue line here. So on our picture, y equals 2 would be up here. So this is now our revolving line. If this is our revolving line, that means that this shape right here that we already have, this guy right here, is going to be revolved around this, so it actually wouldn't, like its reflection would be here. It would get revolved. This thing would end up looking kind of like a ring, really. So if it's going to look like a ring, what are we going to use? We're going to use pi r squared minus pi r squared. So our bounds are still going to be from -1 to 1, and it's going to be pi r squared minus pi r squared. The main question is, what in the world are the radiuses, right? So let's use some different colors here. The big radius is going to be from here to here, right? Or from, here all the way down to here. It's the middle axis all the way to the outer edge of the ring. But that equation is this. So do we have two equations that we can subtract to get this difference? We do. We've got this equation that's brown and this one that's blue, and that's 2 minus x squared. So that's actually that. Then minus pi, and then what's the other radius is the question. So we're going to go from -1 to 1. Well, the other radius is, let me draw it in. How about green again? ignore the fact that this was green. Well, the inner radius is actually just from here to here every time, right? Here to here, because this thing stays flat. So this is our inner radius. So this time, we don't even really need to subtract 2 lines, because we go, oh, how big is that? That's 1. But if you wanted to be like, oh, I got to think of it as this line minus this line, well, it's just the line 2 minus the line 1, and 2 minus 1 is 1, right? So we can just put 1 in here. Wow, those are intense. And you could obviously nint both of those. I'm not going to do that because I think my camera is running low on battery, and I want to make sure it doesn't die. But that is a lot. So my question is, or my guess is we're going to need to do some good homework questions tomorrow to kind of go over some of these volumes. The main thing that's hard is just visualizing. All right, then you get to use nint. Bounds are usually pretty easy, and figuring out whether you're using just a circle or you're using a washer is not too bad. It's mainly just what in the world are the radiuses then if you're trying to visualize it. And I know that can get tough, so we can talk about that if need be. All right, that's the end of 7.3. Great work, peeps.